So today we are going to start talking about data structures. So during the lesson, we will kind of introduce the most common data structures that we can think of, and explain how they're used, how they're usually implemented. And for the assignment for today, you're going to be implementing them. And then hopefully tomorrow we'll kind of go over the implementations and stuff like that. So what are data structures? Can someone tell me what they think a data structure is?
Organized way to store data.
Yes, exactly. So a data structure in CS is a way to organize, manage, and store data. And these data structures enable efficient access, and modification of this data. So inherently, each data structure will have its own pluses and minuses. So each one will have its own way of organizing the data and accessing that data. So depending on what you're using, like what your use is, or your use case, you will use a data structure that will kind of make your life a little more easier. And so why does this matter? We know that different data structures can perform different operations at different speeds. That is pretty much the main thing, is how can we most efficiently get to our data, append our data, store it, do all of this stuff. That is why we care about data structures. So for example, let's say we have an array. So we just have random list of letters. Okay. So what happens if we want to add to the beginning of the list? So data dot, like in JavaScript, there's on shift. And I want to add Q. So what will have to happen for me to add this? If I want to add it into the 0th index, and we already have here, this is 0, 1. This is a bad color to use right now. 0, 1, 2, and 3. And we want to put Q into the first index. What has to happen?
I think in Python you use insert, correct?
Yes, you can insert, so data dot insert, and I think you send in the index, and actually the index and what you want to insert. So 0 and then Q. But what will happen? So if my array is already, it already has something at the 0th index, and I want to add Q to the beginning, that means Q will now become 0. What will happen to the existing data?
They'll shift one index over to the right, each one, right?
Mm-hmm. Yeah. So how many operations would I have to do? So each one, I'm changing, let's say I'm looping through this data to do this. So ignore the fact that these are built in, right? So these two, let's say we don't have a built-in function that allows us to do this, and we want to insert. We are going to have to not only insert the data, but we also have to shift everything. And this operation will be based off of the number of elements in this array. So we'll get more into big O on Wednesday, but this has a complexity of O of n, which means that it will take as many, it will take as much time as there are elements in the array, because if this array had like 10,000 elements and you want to insert to the beginning, you're going to have to do 1 plus you have to shift every other element in the entire array. So this is if we're inserting into the front of the array. What if I wanted to just do data.append? So this is in Python. Where will it add my element?
At the end.
The end. Okay, so this one will just add a new element here. How many operations does it really have to do here?
It's just one. It's O of 1.
Exactly. So here, one operation for these two n operations. And again, n equals length of the data array. So this is the amount of items that we have.
Dana, I have a question. So it seems as though JavaScript has a mechanism to insert something at the start, and it's that Java does not.
Java itself, I don't.
Or not Java, sorry. JavaScript has something to insert at the beginning and Python does not.
Python does. I think insert uses that. So insert, you can specify. Yeah, there's a few built-in functions that allow you to do this.
So for your previous comment, you said there's a cost then where you have to arrange. It's more costly to do insert than it is append.
Yeah, if you have a big array and yes. The short answer is I actually don't know how Python implements their insert, so they might have a more optimized version of it, but the most basic way of doing this would be to shift everything over and insert to the beginning. So yeah, in general, it is more costly to insert in the beginning of an array than at the end of it.
And Zainab, that's a really good point, that Python may have some optimizations. Yeah, first off, like with these very fundamental operations, like inserting to a list or an array and stuff like that, like we need to remember that like the computer, like when we write this code, it's getting run through a whole sort of like the JavaScript virtual machine or whatever the Python runtime is called, that's essentially like compiling this code in real time. And there are all sorts of like clever tricks and optimizations that can happen. And we don't know those exact details some of the times. So in general, with more modern languages like this, unlike say a language like C, where you directly manage the memory that your program is using, sort of the rule of thumb is basically to trust the language runtime, to trust the compiler. The other thing I just wanted to add on to what you're saying is that like when we're talking about data structures or algorithms, both in terms of thinking about problems and also like in technical interviews and stuff, we generally will be doing that at a level of abstraction above any particular language. And the runtime details of a language. Like we'll see later, we're gonna like implement this using Python, and you can implement this in JavaScript. But these are sort of like universal CS concepts. And so it is actually helpful for us when we're talking about these things to not worry about those implementation details. Part of the assumption being that it's like those are not what is going to kind of like make or break the program a lot of the time. Like if we're choosing between two different data structures, like it's going to be more the choice of the data structure that would matter. Yeah, and also arrays in JavaScript aren't really arrays. They have like queue and stack like behaviors, so they're kind of weird and funny.
Yeah, we'll get into
Yeah,
those
sorry.
more.
I didn't mean to jump in. I
Oh, no,
got
no,
excited
that's
about
perfect.
this.
Yeah.
Yeah, is that
We
is
love data structures.
total? No, it's good. Is that some helpful context too for this? Because that is a really good question, and it is really good to think about like the specifics of our what is the language actually doing. Kind of what you want to do is like if you're working on some code and you need to start worrying about like exactly what is more efficient in like adding something to a list or an array, you'll know when that happens. Most of the time, the chances are that if you're trying to improve performance, there are far bigger performance hits in other parts of your program, and it's not going to be these more sort of like basic operations that we use.
Yeah, and it'll make more sense when we're talking about Big O on Wednesday for sure.
Oh, that's a
Because
good point.
we'll go over like,
Yeah,
we'll get there.
yeah. So that's a really good question. And again, the TLDR, the too long don't read the data structures is we're not even going to worry too much about implementation details when we sort of like talk about them.
Thank you.
No, yeah, thank you. Yeah, and this is our first time with this whiteboard, by the way, and it's I hope pretty awesome for folks.
I like it. I used to always use a whiteboard behind me. But okay, so like we said, based on what operation you're looking for, some operations might be faster than others. So this is the case in an unsorted array. Let's say I have a sorted data. And this array has, let's say, A, B, C, and X. So in here, if I want to call a function that will insert, but keep sorted. And then this can take like D, let's say. So if we wanted to value the fact that our data is sorted, then we would have to do a bit more of a complex insert, where we would have to loop through and then find, okay, we have between two elements. So we have the first element and the second element. Is it larger than the first? Yes. Is it larger than the second? Yes. Then we can move on. Then we have our second, we're looking at our second element and our third. Is D bigger than B? Yes. Is it larger than C? Yes. So we will move our pointers over, and then we can see that D will fit in between C and D, and then C and X. And what we would have to do is just pretty much create a new array that, or insert. So we can put C, D, and then X. So we would have to shift one, but this has more complex operations, as you can see. So if I'm inserting something that would fit in here, then it would be quite fast. But if I want to insert something that's towards the middle or towards the end, then it will be closer to like an N operation. But yeah, so it pretty much just is based off of what do you value in your code. Do you, like, if I want to implement something with a list and I don't care about the sorted and unsorted, I would probably just add to the end because that is the fastest way of appending. And then when I'm retrieving, then I would have to look for stuff. But if I want to look for stuff primarily, I would probably want to keep stuff in a sorted array, because then if it's sorted, I can take, let's say, the middle point here. I can look at the middle point and the beginning, and I can say, actually, I can just take the middle point and see if I'm looking for the letter D. I look here, is it smaller than or larger than D? C. It's larger, so we only look at this section of the array. We don't even need to traverse any of this. And this is a type of algorithm called binary sort, which we will be introduced to a little later. But anyways, this is just to demonstrate how there are different use cases for your data, and based on that, you would want to make the best decision for your program. Any questions about this? And we haven't covered any of the data structures yet. No, okay. I'm actually not looking at the chat, I guess, or I just realized. Let me pop it up real quick. There we go. Okay. So there's a quote by Linus Torvalds, who was one of the main programmers on Linux. Thank you so much.
Yep.
Forgot the word.
Thank you.
Yeah, but he said bad programmers worry about the code. Good programmers worry about the data structures and the relationships. So when you're trying to design your code or your program, try to think of how do you want to use your data and what would most efficiently allow you to store it and access it. That is kind of the base question that you would need to ask yourself when you're figuring out what is it called? What type of data structure you're going to use. Okay. So we are going to try to cover the most common data structures. So we will start with arrays.
And I just want to add for folks that these will be things you return to, like, especially when you prepare for technical interviews and over the course of your career. And we're going to be working on these today, but we're not expecting folks to suddenly become experts in these things over the next 3 hours.
Yeah, 100%. Let me just figure out how to hide this. There, my computer's quite a few years old and it's kind of slowing down on me.
It's okay, we're on the leading edge here.
Okay.
Do you want me to
So
grab a power cable for it?
no, it's charged, but
Oh, sorry.
it's dying somewhere. Anyways, so arrays. We've heard the word arrays in JavaScript. They are not the same thing. So we are going to talk about the general concept of a CS array. Thank you for the charger. So an array in CS is pretty much a bunch of one sec, I'm trying to rephrase this. So an array is a data structure that stores data in continuous, what is it called? Or actually,
Location.
in adjacent, yeah. Locations in memory. So I'm gonna do a quick, a tiny segue to how memory works in our computers. So we're not gonna get into the gritty detail of how it actually is implemented, but we basically have addresses that can hold information. So let's say there's this address, and we're just going to give them simple indices. And in each block, you can pretty much put a piece of data. So there's bytes. 1 byte is 8 bits. And a bit is either a 0 or a 1. Again, I don't want to get too much into it, but basically all of our data is pretty much in a continuous play, or like there's just matrices of data. And like, let's say it stops here at 10, here's 11, this point right here, this one's 11, 12. So it's pretty much, if you stretched it out on a line, it would be a line from beginning to end. And we store pieces of information in like code blocks. So let's say I want an array, and that array is going to take up, I have like 4 items in that array. I'm going to take up 4 blocks in the entire memory, pretty much. So I won't get into exactly how many bits and stuff and bytes each one takes. If you guys are interested, I can go into that. I'm interested in that stuff too. But yeah, did you want to say something?
I just wanted to add that the context here is like, imagine that you're a programmer in like 1970 and Java doesn't exist, Python doesn't exist, like JavaScript doesn't exist. Python and JavaScript and PHP and Ruby and Java have something called garbage collection, which is part of like the runtime that runs the program, cleans up all the memory that we use. And so we're sort of like, arrays are sort of like traveling back in time to like, none of this stuff existed yet, and we had to go and create it.
Yeah. And so Adam mentioned C earlier, and in that language, you would have to specify, I would want to allocate enough memory for 4 integers. And you would end up with an array of size 4. That size equals 4.
And we're also traveling back in time to where like a hard disk with like 100 megabytes was big. So like floppy disks and like, you know, like space was precious, and
sure.
Our phones are way more powerful than all of the computers probably put together that existed in 1960.
Yeah.
Sorry.
But yeah, no, this is good. Yeah, so this is working memory, or if you guys have ever heard of the word RAM, this is a random access memory. This is what gets used when you are running your program. This is also different than storage. Storage is going to be where you store your files, your videos, your music, all of that stuff goes into storage. This is your hard drive. And stuff like that. But anyways, so the way arrays are structured is that they take a continuous amount of space in our RAM. So you can access them by saying, like, let's say this address is 3 for this array. If you want to access the next address, you would say access 3 plus 1. which is 4, and address 4 is going to be here. So in my array up here, I had A, I had B, I had C, and I had X. And then here, maybe there's some other data that's like some sort of binary, I don't know, like there's more data here, more data here, more data here.
A sprite image.
Yeah, and a sprite image, anything. So yeah, that's pretty much how arrays are structured in memory. So because of this, when you want to restructure your data, if you're adding to the end and the end is empty, then it's pretty easy. Actually, we won't get into the specifics of that inside memory, but
And
yeah, please.
I was gonna talk about the index.
Yeah, sure.
Yeah, no, this is, I do get really excited about this.
Mhm.
Like, this is a lot of fun for us, as if you folks can tell. So that 0, 1, 2, 3, 4 in the diagram, that's the array index. So like when you're working like with JavaScript arrays and we're talking about the index of them, JavaScript arrays don't really work this way with like specific memory locations, but that's where it comes from. Like in theory, an array index is like a pointer to like where in some contiguous block of memory that element, that bit of data for the array lives.
Yeah. Thank you.
That's it.
Yeah.
Yeah.
Okay. But yeah, anyways, so because arrays are adjacent, accessing memory is easy. So you can have, like Adam was saying, these indices. And so this specific array here will have index 0, 1, 2, and 3. So you have indices relative to your object, to your your array. And this allows you to find things very easily based off of the indices. You can also loop through them relatively easily. Any questions?
And this is a great time for any and all questions.
Yeah. Actually, one last thing I'll add is so when you try to push to an array that's already full, your program has to be able to handle creating a larger array. So this is, again, if you're not using something like Python, like the built-in functions, because they do this on their own. But if you're implementing these things on your own, you have to create a new array that is larger in size to accommodate for your data. And so this kind of gets deleted. You copy over your data, and then plus some more that you added onto it. And that now lives in a different part of memory, wherever the first empty slot was. So if this was an empty slot here, then this entire thing would just start up here. So A would be here, and then B would be here, C, and so on. Questions?
I've got a quick question. So each of the arrays has their own index. So can there theoretically be indexes within indexes in the array, kind of like on your top diagram where you have position 0, 1, 2, 3, 4, and then above 3 you have 0, 1, 2, 3.
So you can keep track of that type of information, but I should have actually done, so this one is going to be like a longer number. So let's say 0, 9, 7, 5, something, something. So the indices here were actually memory addresses. That's what they're called. So this is relative to the entire computer. In your program, you only care about the index of your current array. You don't need to know where it is in memory because you've created a piece of it, or you have an alias for it in your program. So if I had array equals something, this is pretty much pointing to where it is in memory, and then you have your indices relative to this array specifically.
And like what you could kind of do is maybe in one of the elements of your array, you have a pointer to another array. And I think that was sort of what you were asking about. I'm not sure if that's
Oh,
exactly.
okay. Do you mean like nesting arrays? Is that?
Yeah, well, I was just talking, it makes more sense now that you have the longer number there with the working memory.
Yeah,
The
that's,
array index is within that working memory, so that makes sense.
yeah. So like this would be the next one, 976, and so on. Okay, so that's kind of the basics of arrays. We'll kind of revisit it a little when we're talking about a few different things that we can do with them.
Sorry,
I know.
scroll back real fast. I'm sorry, I had a question. So if you made, in that, in your circled example, how you would start that new one at 13, if you made like another array that was like, also took up like 4 spaces, would it start where the old one started? Or where would that go?
I think
Like,
that
what
depends
happens
on,
to the space?
yeah, that depends on the memory management of the machine, I would say. So if it's pointing to like the last piece of information here, then it would go in here. I'm not sure. Yeah, we would have to look up exactly how these things like the memory management is implemented in
Yeah, exactly.
an
Like
operating system.
the operating system, like when you create an array, the array, like the operating system will decide what memory to allocate for the array and give our program like the starting address essentially for that block of memory.
Mhm.
And if it's a fixed size array, like we'll like maybe we'll know that too. But the operating system outside the context of our program decides like where to allocate, what memory to allocate for an array, and then our program just has a pointer to like that location in memory
Mhm.
that everything for the array indexes off of. Yeah, that's a good question. And back in the day when you had to do all this stuff manually, like avoiding like overflows or like potentially overwriting other programs in memory was a real concern.
Yeah.
And that's part of why like operating systems evolved and languages like the ones we use now evolved so that we don't have to worry about this stuff. And because there were massive security holes and problems and
Yeah.
Yeah.
If you want to feel the struggles of having to deal with your own memory management, code in C. That will give you a run for your money.
I never,
I actually liked C.
I only did a tiny bit. Did you do
Yeah.
like a
Oops.
bigger project in school?
I've done quite a few projects with it. Yeah.
Did they have you like build a compiler? I never did that.
No, not the compiler, but we've built like a shell. I've built some networking stuff, like sending over packets and stuff like that.
That's awesome.
Yeah.
That's cool. Yeah, all my schoolwork was in Java and we did some similar things, but I think that would be more fun
Yeah.
to see.
Yeah. Okay, so the second data structure that I would like to talk about today is a linked list. So when we start off a linked list, it is initially empty. So this is okay. This is again a little more theoretical than what it is here. So I'm just gonna I mean what we use today, but pretty much when you're making an array, you usually have a fixed size for that array. Again, like even if you don't send in anything, I actually don't know how, again, Python does it specifically, but
Python doesn't even have it, let us make arrays. It does
well,
lists.
lists, yeah.
Yeah, because that's how it avoids dealing with the fixed.
Yeah. So to define an array, you usually have to tell whatever program you're using how many elements you would like in it. So every time you initialize an array, it has some space.
Oh,
It could also be empty, but then it would only have, I think like one space, or no. No, if it's empty, it doesn't have anything.
Yeah, I think, no, yeah, when you create an array, like you would have to say how big it is, and I think in most languages you have to say what type of array it is, so that each element of the array takes up the exact amount of memory, because like storing an integer might take up less space than storing a character, and so each element in the array needs to hold the same amount of memory.
Yeah,
So, yeah, when you create the array, I think, I'm not 100%, but I think like regardless of if you put something in it or not, that memory gets allocated. So like even if the array is empty, that memory is like reserved for us to put stuff in there.
yeah. So we would define it with the name of the type that we want to put in that array, and then the size. And in, I would call it more primitive languages like C and stuff like that, we would only be able to insert integers into this array. Unlike, like we said, Python.
Yeah, I don't think Python. I don't think Python might let us create an array, but we almost never. I don't
Yeah.
even know if it's there or not.
I mean, like the Python list is similar to what an array is. It just handles stuff in the background.
Yeah, exactly.
Yeah.
Exactly. I see what you're
It's a
saying.
variation of an array.
Yeah,
Yeah.
or yeah, I would say it's like. It takes. Yeah, I'm just gonna jump in, like a Python list takes the parts of an array that are really nice to have, like having stuff in order. And deals with all the unpleasant stuff like memory management and fixed size and things like that. And so a list is like technically a different data structure, because in theory, like an array is this thing with memory, but like JavaScript has something called an array, and like we end up using the words interchangeably all the time.
Yeah, even though, again, JavaScript arrays are not
Yeah,
arrays, yeah. No, this int array, this would be in Java or C. I'm blanking on other languages, but those are the languages that you have to specify type and you have to specify size. But no, so you don't have to do this in Python or JavaScript. This is, so today is more theoretical, and then we'll see some code later on. Okay, so linked lists, on the other hand, so this one starts off with an initialized space in memory. This one does not. This one will pretty much start off as something we call a pointer. A pointer is kind of like when you alias. So here, when I aliased array with ARR, I am pretty much pointing to this array in memory. That is generally what a pointer is, and I won't go too into it unless you guys want me to later on. But with a linked list, so this is just the alias, and you can, this one is not pointing to anything, so this is pointing to null right now if we start off our linked list. And the way we add data to a linked list is we create something called a node. And this node will have our value, and it will have a pointer. This is the most basic one. So our list doesn't point to null anymore. It will now point to the first element. And let's say we wanted to add the letter A. So I'm gonna stick to the ABC example. So we wanted to insert the letter A into our linked list. And so it creates a singular piece of a data structure. So a node. And this node can hold the value of what we want to hold on to. And this pointer, because it's at the end of the list, so this is the beginning of the list, this is technically the end, it's pointing to null, so it's not going anywhere. So if I want to add a new node, so let's say I want to add B, then I can maybe add to the end of this, and so this pointer can point to a new node, and this will be B, and this pointer now points to null. So we call this a singly linked list, because it links each element to one other element. And to traverse this, you would have to start off at the start of the list, and then go hop pretty much from this point to this, and then this allows us to go to the next data point, which is here. There's also a different one called a doubly linked list.
And can I mention
Mhm.
something?
Can I just finish this one?
Oh, of course.
Example?
I
Thank you.
apologize.
No,
Yeah,
thank
good
you.
call.
So with a doubly linked list, we have our data still, right? So we have A, but we have a pointer to previous, and we have a pointer to next. So this one, this is next, this is the value. So here, previous, next, and then we have our val. And so for the first one, previous is going to be null, right? It's not pointing anywhere because it is the first element. And then if we add another one, our next one would be pointing to B, right? This is our second element. Let's say there's nothing next. But this previous one will now point to this one. That way, wherever we are, we have access to the one before and the one after. And that allows a bit of an easier traversal. Yeah, you were gonna say, Adam.
Oh. Thank you, Zainab. And yeah, we're experimenting with sort of sharing a mic, so I apologize if I was jumping in at a bad moment there.
No.
Yeah, I one of the things I think is really cool, like the linked list. So we were talking about locations in memory, and like each one of these like nodes, each one of these items in our linked list could be in completely different places in memory, and it's only like the pointer that knows where the next one is.
Mhm.
So that's totally unlike an array. And the example I like to give is maybe, I don't know, it's like sprite images from a Nintendo game or something. And because it's an image, it like the way the image asset is stored takes up a lot of data. So rather than having to find one big continuous block of data for all these image assets, like the computer can just find whatever parts in memory are available and use pointers in the singly linked list to kind of keep track of where the next one is. It's not the best example, to be honest, but yeah.
I think that's good. For linked lists, there are certain reasons why you would want to do it. So if you don't know, if you don't know how much data you want to use, and you just want to use up data on a case-by-case basis, so like you're inserting elements and you don't want to hold on to an array of a fixed size, then you would use linked lists to allow you to kind of grow with the data versus having to hold on to a lot of memory in anticipation of the data. Questions about linked lists?
I think like a good example for use case for this one would be like a GPS. If you're constantly looking for more, adding more location, you're making more nodes and traveling.
Yeah, I can see that. Now, I don't know how actual GPS works, or like how certain map apps track that information, but that could be a use case, definitely. What else? Any questions? Not a lot of questions today. Okay, so this is the concept of linked lists. So next we are going to talk about stacks and queues, which I believe there are some people who have heard of them before. So stack, think of a stack as, let's say, an actual stack, right? You put an element in. So if you add an element for a stack, it would be called push. So if you push an element onto the stack, let's say I want to push 3. 3 is at the beginning of the stack. And let's say we want to push 5 now. 5 will just go on top. And so on. So 6, 13, something like that. If we want to, and so you can only add to it by pushing onto the top of the stack, and you can only take away from it by taking from the top of the stack. So think of it as like a stack of plates that is in like a cylinder. So you can't grab anything from the bottom. You can only grab the topmost element. So the operation to remove is called pop. So to pop something is to remove it from the top of the stack. And we've seen in Python, there is a pop method, and that removes the end of the list and it returns it. So here, if I call pop, it would remove 13, and that's it. So our stack now is like this. So this one, so stacks are first in, last out. Questions about stack? And you can also see this as going this way. So 3, 5, 6. When you add to the stack, it gets added to the end, and then it gets removed from the end. So yeah, this is how a stack is. The only thing you need extra to implement a stack is a pointer to the top of the stack. And this is usually kept track of by the index. So if we're starting here at index 0, 0, 1, 2, 3, we know that the top of the list here, top equals 2. Because the last index in this array is the second here. That's the last one that has actual information. Now a queue, on the other hand, a queue is first in, first out. So think of it as a restaurant queue. Any line that you're in, that's pretty much what it is. So so we have this queue, 0, 1, 2, 3, 4. So these are the indices, and I add an A here, and then I add a B, and then I add C. So the first element in would have to be taken out of here, and then things are shifted over. So so here we had push and pop as our modifying methods, and here it's NQ and then DQ. And so NQ adds to the end of list. And then DQ removes from the beginning. Of the list. And built into Python and JavaScript, there are methods that can simulate this. So like we were saying above at the beginning, if we wanted to insert to the beginning, we can use the insert method, or on shift, which adds to the beginning of the list. This is JS, this is Python. Okay, questions about stacks and queues?
Yeah, so is a stack,
Go ahead.
oh, sorry, I was just gonna say, is a stack not? Is a stack just a general property that data structures have? Like, cause I can pop off an array,
Yeah,
I can push to an array, but like, I've never worked with a stack.
yes. So
What
these
that is.
Well,
these are specific, so a stack and a queue are specific implementations of an array, a specific way to use an array. You can also use these with linked lists. So if I'm implementing a stack with a linked list, all I have to do is add, one sec. So add to end and then remove from end. To implement a queue, I have to add to end and then remove from the beginning. That is generally how it is. So these, I'm just gonna make a note here. This is hard to read.
yeah, just to reiterate, we could implement a stack data structure using an array or using a linked list or potentially using something else.
Yeah. Those are
And this is also where the JavaScript array is confusing because it does sort of combine like a stack and a queue and an array like behavior all together into
Mhm.
one thing.
yeah.
Like, and that's,
And-
I think, a source of confusion, like I think. I'm not sure if like an array in Java has a pop or an array in C has a pop. I want to say no.
Mhm. I mean, no, so they're not built in. They're never going to be built in. Yeah.
Okay, that
You
is,
have
that is
to-
correct.
Yeah. Usually those built-in functions like the pop and push and stuff like that, it's someone wrote that code. It's in a library. That's why you're able to use it in Python. But if you're programming from scratch without using any of these fancy methods, you have to implement them. So I'm talking about the actual implementation of those things, which now we have access to through libraries.
Hey guys, hi. I'm Ben Cohen. I'm like a instructor here now.
Hey,
I
Ben.
just wanted to. I was listening in, and I just wanted to give my input. Something that I don't think was mentioned was the difference between a what do you want to call it? A data structure and sorry, I'm blanking right now. What's the difference between like basically the implementation versus the idea of it? A data structure versus a sorry, I'll write this up. I don't want to waste your time in class, but
No,
yeah, all right, thanks. But hi.
thank you. Yeah,
Good to
yeah.
see
Jump
you.
in when you're ready.
Yeah, and that is a really good point. We've sort of mentioned it, but to kind of take what you're saying and or actually, I don't know if you want to run with it.
You
We
can, it's fine.
Yeah, we sort of mentioned it, but yeah, like just like the example, like you were saying, Zainab, of like you can implement a stack with a linked list, like it becomes really helpful to. Now I'm blanking on
Sorry.
words. Separate the idea and these concepts from how we actually like write it in our code. Like an example would be like if we're writing a program and we know we need to loop through something, well, we can use a for loop, we can use a while loop. There are a bunch of implementations of our loop. Kind of similarly, we can have a bunch of different ways of implementing these data structures, but it becomes really helpful to be able to think about them without worrying about the implementation. And I feel like I just totally butchered that too. So I'm gonna pause and hand it back to you.
Okay, thank you. No, you didn't. It was, yeah. Louis, you had a question earlier?
Yeah, I was about the stack. So if I want to remove the first element, I would have to remove all the elements from the top first, then to get to the bottom.
Where? Here?
For like stack. For
So
stack.
stack is a way of, or it's, I guess stacking is an idea. It's stack. All you have to know about a stack is that you can add, not all you have to know, but an important thing to know is that for a stack, you can only push to the end and you can only remove from the end or the top.
Yeah.
So we call it.
Yeah. So like for like the number 3 you got right there as an example, I had to get rid of the 6, 5 to get rid of the 3, right? I cannot just go around it.
Yeah, exactly. So you would have to remove so top right now is 6. So the only element that you're able to move is a 6. And then top becomes 5, and then you can remove the 5, and then you can remove the 3. Yeah, you're right.
Is it like, so I brought up the Hewlett Packard calculator thing earlier. If you complete a calculation of 4 plus 4, and now 8 goes into the stack when you're done, you can complete another calculation of 5 times 5. Now 25 goes into the stack. And then if you're ready to add 25 to the number you just put in previously.
Yeah,
So you kind of drop them out of the stack as you use them, don't you?
Yeah, so in your case, it would be like you're removing elements and then replacing 2 of them, but by 1 element that is the product or something like that.
And yeah, I think it can actually get really interesting to like write a calculator using a stack. And kind of like you were saying, we could either store maybe the operations in the stack, or we could store like the output of each operation in the stack and then pop for undo.
Yeah. Yazid, got a question?
Yeah, I just want to put your attention on your explanation on NQ and DQ. It's different for what you have on GitHub on README. So it's kind of like confusing, but I think what you have written down here is the correct answer.
Could you say that one more time?
On your README on GitHub, NQ is dealing with the beginning of the list, and DQ is dealing with the end of the list, which is different for what you from what you have here on screen.
For stack or for queue?
For Q.
Queue.
You
can only add. Oh, yes. Okay. I do have it. I have it opposite. My bad. Yes. So NQ, you're adding to the beginning.
I thought that what you have on screen is the correct answer, and on GitHub is the wrong answer.
Yeah.
Because when I Google it, NQ is dealing with the back. You have to put it in the back.
Yeah.
And the DQ is the front.
Yeah.
So what you have on screen is correct, but on
GitHub.
On
GitHub, okay, I'll update it. Thank you.
Thank you. I will see if I can do that right now.
Okay. That is, yeah, thank you for pointing that out. Okay. Sorry, I lost my
Yeah.
my
and
notes.
These are great questions, by the way, folks. So thank you and keep them coming.
Oh, I hate this thing. Any other questions?
Oh, you might.
Yeah, that's it. Yeah, I was gonna stop now.
Good call.
Okay, so let's take oh, Benjamin, do you want to talk about what you found? Or what you want to say?
Yeah, sure. I was just, am I still on camera? Yeah. I was just talking about the difference between a data structure and a data type, which is a very, it's a subtle difference, but essentially a data type is something like an array, which is something you know about and you have, it's pre-implemented in the language. And a data structure is an idea basically where you can use existing data types to build up an abstraction. You can say it works specifically this way. The only input is a push or a pop, but it's based on arrays because arrays are built in. But the weird thing is that an array is also a data structure. In another language, you might have to implement array yourself. It's not necessarily fundamental.
Yeah.
Yeah.
Thank you. Thank you for the input. Okay. Do you guys want to come back in 15 minutes? So this link is at the bottom of our lesson for today. It's in the resources. It visualizes different types of data structures. So like here with a stack array implementation. So we have an empty array that's already been initialized. Like we said, we start with a specified amount of empty space and we want to add to it. So we push on 3 to the stack and our top gets updated as 1. That means this is our next available slot. So go ahead and push 4. It also gets added to the next one and so on. And then if I want to pop, it takes the top, decrements 1, and then accesses that index, removes it, and now we have an updated list. And if we want to pop again, it does the same thing. Sorry, I just realized it was kind of small. So that's an array implementation with a stack. You have a linked list. If we notice here, it's different than the array because the array already had data, or not data, sorry. It had a space in memory. It had stuff already populated, but here we start off from scratch. If we want to add a node with 3, it adds onto it, and this is the top. We add another node 4. So it adds it to this part. So I'm actually not going to get too much into the implementation because so the reason why it's adding it to actually no, this is so this is the top, so it keeps track of the end of the list pretty much, and it keeps adding so this is our first element that we inserted, and so we don't have to keep track of too many things. We have access to the top of the list, and then we can just push to the top of the list. I want to add another value. Yeah, there we go. Yeah, this is just a cool tool to kind of see visualizations. There's also queues, and queue. And let's say I add another one, and queue adds to the end of the list. If I dequeue, it removes the beginning one. If I enqueue again, it adds to here, and then if I dequeue, it'll take from the beginning of the list. Questions? I just wanted to share this. Okay. Stop sharing here.
Where is that slide again?
It's at the bottom of our curriculum.
Okay.
Okay. So now you guys should be able to see my screen over here again. All right, so next thing that we're talking about today is a hash table. Hash table, sometimes it's also called a hash map. So this data structure allows you to create a list of key pair values. And after creating a pair, you can retrieve that value using the key to retrieve it. So let's say we have an array here or a list.
Are we recording?
Yes.
Thank you.
0, 1, 2, 3, 4, 5. So if we want to add to this data structure, we can use we can access the elements by using the indices. But what if we have data that we want to access using a key? Think of Python dictionaries. So something where you have a key and this will map to a value. So with hash tables, we usually have something called a hash function. And what this hash function does is it takes in a key, or it takes a value, or I'm not going to call it value. It takes in a key, and then it transforms it into an index on our array. So this index will be one of these. So this key doesn't have to be a number that fits within the indices. So here we only have 0 through 5. This key can be Apple. And then we send Apple to a function that gives us an index relative to the size of our hash map. So I will actually show some code for this. Which desktop is that? This one. Okay. So let's create a hash table. Let's see. This switching back and forth between cases. Oh, let me. I was going to do this earlier. Forgot. There we go. Okay. So we're going to create a class hash table. And we're going to define an init function. And to restart this. So our hash table is going to contain a table. Hold on one sec. Technical difficulties. Okay, so I'm going to create a table, and this will be let me actually, okay, I'm going to implement this in JavaScript because your homework today is doing it in Python. So let's do this. We're going to create a class hash table. We have a constructor. And this is equivalent to the init method. So we can define a table. And this table is going to be an array. So new array of, let's say the size is 64. I want 64 elements and I want to fill them with zeros. So if I and array. So this is one way of you guys have seen JavaScript functions. So if I want to print the array, I can just do console.log. Table. I could have actually just created an instance. So my hash table equals new hash table. Okay, so I'm creating a new hash table, and then I can say my hash table dot print array, and let me just go to the right folder. Okay. And here we go. We have now an array of size 64 with all zeros in the beginning. So there's no values. So a hash table is supposed to hold information, right? So let's write that mechanism. Let's try to get it to set a value. So in here, when we want to set something, it's going to take a key, and then it's going to take a value. And then it'll do something. So like I was mentioning before, our hash table usually has a hash function. So I'm just going to call it hash, and this will take a key. And what this function will do is transform this key that we sent over and return an index based on our index size or our array size, our table size. So I can say we can start off with hash is equal to 0. This is a common, I would say, a little algorithm to create a quick hash from a certain key. So I can say I equals 0. So I'm just going to loop through I is less than key dot length. And oops, I forgot the incrementer. I plus. Okay, so this is going to loop through the size of the key. So let's say key here is going to be a string. So it loops through every index of that string, and then it's going to add the numerical value of that character. So we have in computer science characters. So if you had like a string like this, each character has its own numeric value on the ASCII table. So ASCII table, I forgot what ASCII stands for, but it's pretty much just one C. ASCII table. It tells you how letters and characters are defined in program. So the character, let's say I wrote an uppercase C here, an uppercase C, then its decimal value is going to be 67. So what this is doing, it's just taking the numerical representation of whatever character it is, and then it's adding all of those up. So that way we can come up with a semi-unique hash, and it would also be reproducible. So every single time you get a key that matches that key, you should get the same exact number back. So what am I doing? Char code. No, char code at. And then I'm going to say index I. So it's taking the actual key that was sent in. Let's say for now it's Apple. It's looping through every letter. So A-P-P-L-E. And it's taking each letter, converting it to a number, and then adding it onto here. A lot of hash functions already exist. So you might want to write your own to make it more unique or harder to crack. So you can, hashes are also used in passwords, which we will talk about when we're talking about authentication and stuff like that. Okay, so now we will return hash. But we do have an issue where this is supposed to be an index, right, to an array. But our array only has 64 items. Does anyone know how you can get a number based on this? So this number, I'm assuming, will be pretty big. It will be, because if one of the characters is 64 and you're adding, or like 67 or something like that, that's the value of it. If you're adding it up, it's going to be a couple hundred. So how do we return a value that will fit in to our array? How can we transform this hash? Do you guys know any operations that might help with that? Or operators? No?
Create a dictionary object in each position.
You mean big int?
Not quite. So this is an operator like minus or plus or equals or divided by, or what's another one?
The modulus one?
Yeah, so mod, I'll explain exactly how this is going to work, but we can mod it. And this allows us to, we're going to mod it by the length of the table, so by 64. So what mod does is it returns the remainder of a division, pretty much. So let's say our hash was 7 and our table length was 5. So it's going to be 7 divided by 5. The remainder is going to be 2. And so this number will be 2. So this gives you the remainder of a hash. And it will always be within less than 64, because if it was 64, then the remainder would be 0 if it was divisible by it. So this is how we can guarantee to get a number that is always within like a number range, pretty much. Any questions on this? I know this one's a little confusing. Maybe, might not be. If anyone has hands up, I cannot see that screen at the moment.
Can you scroll back up real quick to see the initial set? Thank you.
Yeah, so this set is not done yet. But yes, this is our.
Can you explain the hash key, the hash function?
Sorry?
Can you explain the hash function? Say one more time.
You said, why did I put an underscore here?
No, can you re-explain it? Can you explain it again?
Explain it, yes. So the hash function is supposed to take in a key, and this key can be anything. A lot of times it's a string, and it takes a key and it produces an index that will fit in our hash table. So in this array that we created, this function will take a key and will return an index that is going to fit inside of our array. That way we can access, we can use that array as kind of like an access point. So if I were to look up, if I were to add fruit as a key and then apple as a value, what my program should do is take fruit, send it into the hash function, and retrieve an index that it can then put the value in. Does that make sense so far? It'll make a little more sense once we see it all running, and then I can redo the drawing as well.
Why did you put the underscore there? Is that just to make it private?
No, so there is a practice where you can put helper functions with an underscore in front of it. So this is a specific helper for the hash table. You don't have to do this.
Okay, gotcha.
Mhm. Any other questions? All right, so now that we have a hash function, and this hash function, like I said, will take a key, will return an index that will fit into our array, or that will be able to access any of the array's indices. So let's actually set the value here. So first step, we are going to grab the index, and we can grab the index that we need by calling the hash function. So this dot hash, and then we're going to send in our key. So the hash returns an index, and then all we have to do is do this dot table. So we're accessing the table here, and we are going to access the index that we have now. And we're going to set the empty slot to whatever value that I wanted to add there. So forgot here, it's push. So this is a list. Actually, no, I'm not pushing. What am I talking about? It equals the value. So questions about this part?
When you're finished creating a hash table like this, would that allow you to search for, say, like fruits and apple again? You can search for it by a string key, but you could also use the index. Is that what we're left with at the end?
Yes, but typically you're not going to use the index because it was built to be able to handle a key value relationship.
Okay.
So it's like map,
I'm
it's like
following.
a dictionary. Yeah, it's like the dictionary in Python. So you can technically access it, but yeah, you can only access it with the index if you hash the key. So the point of this hash function is to reproduce the same index for the same key. So I don't want any randomness. I don't want to input fruit one time as the key and get an index, and then input fruit again and get a different index. That will defeat the whole purpose. So the hash table allows you to have a quick lookup for items in an array or in some sort of data structure.
So Zainab, I've commonly heard the word hash when you hash a password or hash a secret. What is the word hash and how are hash tables used? And maybe that's what you're describing now, but what are we doing here?
So hashing pretty much is taking in an input, taking in something and then modifying it in a way that is reproducible. So if every time you modify that same value, or the same, like here we're calling it key. So every time you modify this key, you will get a certain result that is the same. So here in the case of a hash table, we want an index. So that's why we're just pretty much doing an operation on this key. This will produce some sort of number for us. And then we're returning a number, that number relative to our table length. But for hashing passwords, that the function would take a password and then do a bunch of operations on it to change it and modify it so it's not, so no one can detect what that password is. Generally hash functions are like a one-way operation. It's pretty difficult to figure out what that hash was if you don't have the original function, that original algorithm. But specifically with passwords, there's like password cracking, which pretty much you have a hash and you're trying to recreate it by using certain words, and that's how you can figure out what that password is. But we'll talk about that at another time.
Why are you trying to create an index when this object already has an index of 0 through 63?
Because so we're creating an index based off of the key. So this example will actually make it more. So if I'm adding fruit, so this is the key, and then the value is apple. So when I do this, oops. So here we had an empty array, but then when I added it, it somehow translated, it translated fruit to an index. That's what it's doing. So if I printed, where is it? So when I set, I'm just gonna do a console log of the index real quick. And then I'm gonna add the index. So I'll do this. I can actually add a few more. I'll do fruit, and then I'll add cars, let's say, yeah, something like that. So what will we see here? And then let me print the array actually one more time. Okay, so all here. All right. So we had an empty list when we tried to add fruit with apple. So the key is fruit, the value is apple. It transforms the key, which was fruit, into a number. For here, it gave us 42 as the index. So fruit equals 42. When we tried to add car, then our index was 41. So if I add different words, it'll hopefully come out to a different index. We'll talk about collisions in a bit, but let's say there are no collisions and the indices are unique, then you will be able to access the elements based on a word, pretty much. I don't have to know the index inside this table. That's what makes it powerful. Did that answer your question? Did it kind of make sense, Jim?
Well, I guess now I have more questions. Was it a coincidence that it ended up before, and what prevents one index from overriding another? I think you're talking about the collision control.
That's collision. Yeah, we'll talk about it in a sec. But so far, just the concept of you're trying to add a key value pair and you want it to be quick, like you want it to be easy to find, so pretty quick to retrieve. And you also don't want to have like an infinite amount of memory saved up. So there are many, many words in language. So you can't have an array that will hold a value for each one. That's why we're using hashes. we hash it into a number that is manageable, pretty much. And when there's a collision, then we have to handle that. So if I input a different word that has the same exact index as apple here, so if it's, I think anagrams will give you the same index. So then it will replace it in this case, because all I'm doing is setting that value to that index. Michael?
So I'm seeing how we're seeing the whole entire index, the whole entire table, but how do you find just that specific one? How do you find apple with fruit?
Yep, so that's what we're gonna do next.
Gotcha.
So we have a setter function, so we can set a value into our hash table. We can also have a get where we only send in a key. And then it should return the proper thing that we're looking for. So the getter, we have to also create an index because our data is saved in an index. We have this neat hash function that will transform any key into an index. So I'm going to create an index based off of the hash function. So I'm sending in a key. And this gives me the index that I'm looking for, pretty much. And to access it, I would have to say return this dot table dot, or sorry, at the index. So our table will return whatever's at that index, and it should be the correct information. So let's say we know here from our print statements that there's fruit and cars that will give us different indices, so we can try to access both of them actually. So my hash table dot get, and we'll say get me cars. And then we'll just actually print this out.
Is set and get, are those keywords for what we're trying to do when we name the function?
Yeah. So this is just, allows us to, I think so. This is the general convention of doing it. Some people might name them differently, but I think get and set are pretty common. Okay, so cars and then fruit. So what will happen when I run this? Here we go. We were able to get our car, and then we were able to get our apple, which was under fruit, just with this neat hash function. It pretty much just transforms whatever key we're looking for into an index that allows us to grab our information quickly. So you see here when I'm just accessing this straight away. I don't have to loop through my entire array to look for it, even though I started off with a key. So I didn't start off with an index. If I knew the index, then the hash table wouldn't really be useful for me, just because I already know the index. I don't need any of this fancy stuff. But because I want to use a key value pair, we had to find a more clever way to save this information. Any questions about this before we talk about collisions and stuff?
Why is this being done in JavaScript as compared to Python?
Because you're implementing it for the exercise in Python. So I figured to show you a different perspective or a different way of doing it, pretty much. But this can be implemented in any language. Again, this is like the general idea of a hash map or a hash table. So there's different like slight variations in the implementation, but it's the general operations are the same. where you grab a key, you get an index from it, and then you access the information. Okay, so collisions. So what will happen when we put two words that have that will have the same hash? So let's say I have just gonna say this one's name. And then I'm adding a new key value pair, and the key is main. So this is an anagram. And since our hashing function is going through the letters and adding up their numeric value, that means this will equal to this, and it will cause a collision. So if I say line, I don't know why. So if I try to access name, we'll most likely see line. Yeah, there we go. So what happened here is we got the same index for both of them. And yeah, see index 33, these were for these two. And so it got overwritten. To not have it be overwritten, what do you guys think we could implement into this? Or add into it?
You can just use another word like fur or hair, or add like a main underscore A, main underscore B, or something like that.
Okay, but let's say that we have no control over that. A user is inputting data into our hash map, and they should expect to get the correct information.
Is this the same because it's the same number of letters, or because it's the same letters only in a different order? What if you were to do tame, or yeah, T-A-M-E?
It's because it's the same letters in a different order.
Okay, gotcha.
Mhm,
So is the order important also, or is it just the same letters?
Just the same letters, because it's adding it up. It's like N plus A plus M plus E. It's going to be the same as M plus A plus N plus E.
So this is all based on the character codes and why it may collide.
Exactly. So if they have the same exact letters but in different order, it won't matter because we're gonna still get the same exact hash value. So there is bound to be collisions. Let me share 1 sec. Okay, let me stop sharing here. So we saw that if we insert something, so let me, yeah, I'm actually gonna draw another one for an example. So here we had 0, 1, all the way until 64. Or sorry, 63, because indices. This is 33, index 33. So if I call the hash function with name, I get 33. If I do the same with main, I get 33. So there's a few ways of doing this. One way, if we're trying to, so the value for this one is lion. So lion is our val. And then for this one, I think Kia was our val. So what it does, when it gets to this line here, we can add it to a list. So for here, we can actually create a list at this index. And this list will then hold the information that we would need. So I'm trying to think. So usually it's added. So here, this will hold Kia. It's kind of small. So when it gets to 33, it'll add it in the first available place, and then it'll add lion on the second one. I'm trying to remember how we iterate. Yeah, this I'll need to look more into collision. What is it called? Resolution.
Collision, yeah.
Yeah. So one way is that we create arrays or lists for each item in our list. So instead of this holding a value of Kia here, it's actually going to hold an array that will hold all the names that fall under 33. Another way of doing this is, instead of having an array that's built in like that, we have our thing from 0 to 63. Let's say here we got to 33. Instead of having an entire array that's predefined with size, we can use a linked list to just hold this node. So the first node would be Kia, and then the second one will be lion. And then this one is not pointing to anything. So yeah, these are just a few different approaches. We won't really go over the implementation of this, maybe when we're reviewing the exercise, but for now, there's some more content that we have to get to. So yeah, questions about hash tables?
So when we're assigning something to 33 there, our function is automatically handling this, or did I miss that part?
Our function right now, as it's written, it's not handling collisions.
Okay.
Yeah. So we would have to handle the collisions. So the way, let me actually write a quick way of doing this. So instead of having a 0 value here, I can actually do, so I can map each index of this array to a new list. So I'm going to use the map function because it makes it easier for me.
I don't think we can see your screen.
Oh, I'm on the right. Okay, sorry. I was on the wrong screen. Okay, can you see my screen now? Yeah, okay, cool. Thank you. Okay, so I am going to map through, and for each element that I have, for each element in this array, I am going to do something. This is the general syntax of the map in JavaScript, if you guys haven't seen it yet. I know we went over it in Python. So you map each element to something that you want to do. For here, I'm just going to return an empty list. So in each element, I want to replace it by an empty list. So right now, if I just print out the empty array, I should see, instead of zeros, instead of zeros, I see empty arrays. So now, our hash function shouldn't change at all, because all it's doing is taking a key and returning an index, and the index is still relevant to this array. When we're setting an index here, we can do, instead of simply assigning that value to that index, we can say this dot table dot or at that index. So we have an array, right? So we access that index. Let's say this is the one that we're looking for here. This is also an array. So an easy way to add to that is just I think in JavaScript it's push. In Python it's append. So you can just push whatever value you want. Actually, sorry. So in this case, we do want to push the key and the value, because if we just had an array of values, there's no way of us finding the key because the key is not saved anywhere, right? So we can actually create a key value pair in here. So we can push key and then the value. So now if we append fruit and apple, let's see what happens. Oops. So now we have apple. But I think I might need to put it in square brackets because it's script. So here I would create a tuple. If you guys remember tuples that we used in Python. There we go. So now at this index, at whatever index we had just created, 42, right? We have at the 42nd index an array, or let's say a tuple if it's in Python, that contains both the key and then the value. So now if I have a collision, it should still push it after it. So if I have something else that's gonna be on index 42, it's going to append it to the next one. So if I do, I know these two will cause a collision for sure. So let's comment these out. So we're gonna add them and then we're gonna see what the array looks like. There we go. So now this is the top of our array. We know that there was a collision at index 33. So now we have two records. One of them contains name, one of them contains main. And so this helps us when we're looking for something. So if we want to get, instead of being able to just access that index, so the index was 33 for name and main, instead of just saying, okay, return everything at index 33, which it will return all of this, but we want to return the singular record or the value. So we can actually loop through it. One sec. Data. I think it's of, right? Yeah. It's dot table. At index. So we are going to loop through this table, the table that is at the index that we're looking for, because we already grabbed the index. We know the index is going to be 33. We loop through these items here to find what we're looking for. So in here, if data at 0, so data at 0, that means this is data, right? Because we're looping through the items in this bigger list. This is going to be data up here, and then at the 0th index, that is going to be our key, and then the value is going to be at 1. So if data at 0 equals the key, that means we will want to return data at 1, and this will move. So this one was for the direct access. And so this should handle our collisions. So if we want to now look for something with name, instead of giving us lion, it should give us Kia. Because before it was giving us lion. Wait, yeah, name is Kia, okay.
Zainab, I have a
Uh-huh.
question. So, I expect that name, or I'll do AEMN, all have different character values, and let's just call them 10, 11, 12, and 13. If the sum of those is, what's the math on that? Is that 40, 44, whatever? If this, or 47, whatever the math on it is. The sum of that's 47. There could also be other characters that add to that amount.
Mhm.
I'm perplexed about if that is that true?
Yes, there could be. Yeah, so you won't just get collisions by having the like anagrams. You can have a collision by having let's say one of the keys was name. Because so let me add this. Name. So it's pretty much doubling the value. But because it's modding it by the size of the table, it's going to end up being the same thing. It's like saying 12 divided by 6 versus 6 divided by 6. Or sorry, 12 mod 6 is going to give you 0. 6 mod 6 is going to give you 0. So both of them will give you the same index, even though they're a little different. So it's just, yeah.
Is that correct to say that Jim's scenario would produce another collision?
Yes. So it would produce another collision. Oh, so
What if you were to use the example of M, N, B, and A, B, C, D?
just anything that you input, it could cause a collision and it could not. So all you have to worry about is, are you handling that collision? So now in our code, we are handling the collision because we are, if we get to a point to an index, and whether something is there or not, we're just appending that information on there. And when we want to look it up, it allows us to look it up. So one possible issue with this is if your hash function was somehow very, very bad, and all the indices, no matter what the key is, it's giving you 33. That means even though you were able to access 33 very quickly, you still have to loop through every single element on that list. And it's exactly, it would be the same runtime as if you were looping through an array looking for items. So that's like a possible drawback of a hash table, but that usually only happens if it's not implemented too well. So if there's a lot of records on one of the indices, you might need to change your hash function and make it better, pretty much. Whoever has their hands up, please speak. I don't have the thing up.
I got a question really quick. Are we gonna start running into like reoccurrences once you hit over 64 keys, right? Do you start duplicating, even if like the numbers aren't the same? What happens once you have more than 64 keys? Since it's a table of 64.
So that's the thing. Our hash function will never return anything above 64. So when we created our hash value, right? This is going to be some unique number. But to guarantee that it is within our array bounds, we mod it to get pretty much, it's just giving you the remainder. So it's giving you an index that will fit within the boundaries of your array.
Yeah, just to add on, and this is awesome, by the way. Yeah, we've designed this hash table, so it's got 64 buckets, and we wrote a little math to make sure that we always put something in one of those 64 buckets. But there's only 64 buckets there because of how we designed it.
There could, yeah, thank you. There could be any number of buckets.
So once you hit over 64, even if they're not the same number, you can get collisions, even though they're like, say they're not equal because you only have 64 buckets. So you got to put them somewhere, right?
So it's what is going over 64 here
Nothing.
in your example? No, I mean, like, are you saying like the key when we're creating the hash?
Right. Say you have more than like you make 64 over 64 keys.
Oh, it
And
doesn't
so-
matter because we have we're handling collisions. So even if we get multiple index twos, we're just gonna add them onto that array in that bucket.
Okay, cool. That's what I was figuring. I was just making sure I was thinking of it correctly.
Okay, yeah, definitely. Thank you. Who else has their hand up?
Yeah, the keys in the buckets now aren't the exact same thing. Like we can have multiple keys in one of our 64 buckets.
Yes. Which is what we saw here
Yeah.
with these ones. Yep, exactly. Yeah, other questions? Yeah, we're gonna break it down.
So if you changed main to name and you
Uh-huh.
put name in twice, what would happen?
Let's see what that does.
Good question. Yeah, someone had that question too. Essentially, like, can we overwrite a key value?
You could, so you would have to handle that in your design here. So right now, what this will do is it'll push a new key. So we'll have duplicate names.
Oh, we will have duplicates.
Yeah,
Oh,
yeah.
yeah, okay. Yeah, that's a really good point.
Yeah, so now I added 2 of them. Actually, I should just change this one to
Yeah. And I am rusty on this stuff. My guess is that for any sort of hash table implementation, we would probably want to check to avoid having duplicate keys. Because
Exactly.
that would be a problem.
exactly.
So you would have to decide, do you want the behavior be just to overwrite or just to like return an error or saying like, hey, like key already exists or something.
Yeah, exactly.
Yeah, and both are equally valid options. It would just depend on what you want to do with it. Like if this hash table is in a pretty protected part of your program, maybe overwriting is fine because you've got code elsewhere that's checking stuff. So by the time stuff gets here, you can kind of trust it. Yeah, sorry to
that makes
jump
sense. No, that makes sense.
Yeah, great question. Great questions.
Who else has their hand up? Kenneth.
On a really large scale, is this the kind of implementation that happens like whenever we try to make a new email through like Gmail? Are they kind of doing the same sort of thing? I'm just trying to think of a real life application on why hash tables exist.
Hash tables exist for easy lookup. So the same
Just
way.
easy lookup.
Yeah, easy lookup, it also, in a lot of cases, saves space if you are, well, I mean, no, the space would be the same. It actually might use more space than you need, but it is more for a quick lookup. Like the reason why we use dictionaries.
Do you think a Python dictionary is implemented with some sort of hash table?
I think
or
so.
hash map?
Yeah, I think it is.
Yeah, like a Python dictionary is probably implemented with a hash table or hash map.
Yeah.
But yeah, figuring out like, is this email name unique for some very large number of emails? That's potentially a use case. Like the relational databases that we see, like Postgres, I'm pretty sure are using hash tables somewhere for all sorts of stuff.
Yeah, for indexing.
Yeah.
Yeah.
Yeah, it's not a real hash table, I don't think, but there's a common tool called Redis that's like a key value store that's like used for caching in web apps. Yeah, exactly like you said, fast lookup. The truth is, stuff these days, like the libraries are so powerful that like we rarely write this stuff ourselves, but you do see like especially when we get into React, like we'll be doing lots of key value lookup stuff, and it's like these concepts become useful. And Benjamin, I think, said this is sort of like the bread and butter of computing, and it's really good to know. And this is, it's sort of like the keys to the kingdom. Like this is like core knowledge that you can like build on for your careers and use to like really build your career. Like we're kind of learning like carpentry skills, but then this is also kind of like
This is tools.
yeah,
That you can, yeah.
exactly. This is tools that will like help you and like as you start like getting into more technical stuff later on in your career will help you with that. And also, to be honest, with technical interviews.
For sure.
Yeah.
Is this for highly transactional and disposable data? So you would read in a set, make a decision, make a calculation, and you dump it in microseconds time?
Depends.
Yeah, it depends. I think this is more optimized for lookup.
Yeah.
So this is for stuff that you want to go back to. This is not information that you just throw somewhere in the back of a server.
Yeah.
It's something that you want to retrieve.
And the truth is, like, once you start, like a database, for example, like, I don't know a ton about relational databases, but it uses some kind of tree structure to store a lot. But then they also have indexes for faster lookup of the things that the database sees is being looked up the most, or that like we as the programmers specify, and it might use hash maps for that. So all these things get like used together and end up getting used in like very, like there ends up being a lot more complexity that gets added on, and it ends up being like very specific to the use case. I guess actually a good analogy would be like, this is sort of like, imagine that we're saying like, this is how internal combustion works. But then if you go and you look at a modern car or a modern jet engine or like a modern motorcycle, those engine designs are going to be dramatically different based on all sorts of real world considerations, even though they're using a lot of the same principles.
I agree. Yes.
Yeah, it's a great question. Yeah, the truth is that this is like a very like conceptual introduction, and that the practical application adds a lot of layers of specificity and complexity.
And yeah, the Python dictionary is a hash map or a hash table. I just looked it up.
Oh, that's awesome. Yeah, I think you can actually find like the C code or the C++ code that Python's written in.
Yeah.
If anyone's really curious, and then you could like look at how they actually wrote it.
Yeah.
Um,
Any other questions before we go on a little break?
yeah, great questions, folks.
Can you find stuff just finding the hash, like just the index number? Like, I know not really maybe in this example, but if you're like, I just want to know what's at 33, and you could just implement that in some way, is that viable at all? Or
Yeah, you can just access it directly. If you have the index, you can check what's at that index. You would be able to. Yeah. So that just would be like using it like an array, pretty much.
Yes.
Okay.
Though on that note, I do want to say, I think part of the idea when you write a hash table that's going to be used in other parts of your program is you might not want to expose that index.
Yes.
Like that sort of abstraction and encapsulation is part of the benefit of this, so that like you probably, like if we had this class and then someone else imports it, like if this was Python, or like the index would be a private variable, and the idea is that in your program you can interact with the hash map and you don't have to worry about how it works under the hood.
Yeah, it's exactly like the dictionary, where all you have to worry about is the key and value, and you almost never use the index. There are some cases, but
Can you access the Python dictionary index?
I think so.
Oh,
I think
cool.
it like creates indices.
That's cool.
don't
That would make sense. Yeah. You probably wouldn't want to most of the time. And if you found that you needed to, that might be a sign that you need another
array.
tool.
Exactly.
Yeah.
Yeah, that's true.
Yeah, that's a really good question. Yeah.
Michael?
So this hash table, is this an array list or a linked list? I don't see how this is a linked list.
This is an array list. I'm not making this as a linked list, no. Yeah. Other questions? No. Okay. Let me stop recording. Okay, so another data structure that we're going to talk about is a tree. So basically, a tree is a structure that has a root node. So this is where we can give it an alias. We access it through the root. And let's say this root node has a value of 9. So what a tree is, it just has nodes, and then it has children. And then this child can have nodes as children. So it's just a hierarchy pretty much. Trees are pretty powerful. There are different types of trees, and we won't go over all of them. But there is something that is called a binary search tree. That is pretty common. So binary search tree is a special kind of tree that has a root node, and it has at most 2 children. It could have 0, it could have 1, but at most it will have 2 children. And actually, so this is just a binary tree. Let's not get into the search one yet. So binary tree means that you can only have 2 nodes. I think there's a ternary tree that has 3 nodes at most. But yeah, so binary tree only allows you to have 2 nodes. So this one can have 2 children. This one maybe only has 1, and then this one has another. So that's a binary tree here. We also have a variation of this binary tree that is called a binary search tree. This is going to be a tree that is ordered. So all of these nodes will likely have information. So let's say this one is keeping track of I don't know, let's just give them numbers. So this has a value of 10. This one has a value of 5. This is 2. This is 7. This one, let's say, is 11, 15, and then 14. So a binary tree pretty much is just a binary tree that is ordered, so you can traverse it. You can traverse it pretty quickly. So everything on the left of the base node never mind. Okay, so everything to the left is smaller. Everything to the right is going to be bigger. This is how you can keep track of an ordered list. So if you see here, 5 is smaller, 2 is smaller than 5, 7 is bigger than 5, but smaller than 10. So if we were to add a number to here, so let's say I want to add 4. So 4 is smaller than 10, so we have to go to the left side. 4 is smaller than 5, so we have to go to the left side. 4 is larger than 2, so we have to put it on the right here. And this is how you can traverse it, this is how you can add an element to it. It makes it easier to add an element, and it makes it also easier to search. So if you want to search, I'll show there's like binary search. I'll show an algorithm of that on the Big O lecture. But pretty much it's so much faster to look for something because you know you're looking for the value 7. You know exactly where to go from here to look for 7. So 7, smaller than 10, larger than 5. There we go, we found it. So the benefit of the tree is if we had all of these in an array, so we had 2, 4, 5, 7, 10, and so on. So like all of these are ordered. We still have to go through from the beginning of the array until the end, till we find number 7, right? But here, at most, you will be looking, you would go down a path that is the size or the height of the tree. That's at most the traversal path that you would have to go down. So when these trees are balanced, which means that the height is like the difference between, I won't go into this, but there are something called, I think ABL trees are balanced trees. Anyways, it's a different type of tree, but also binary search trees can be balanced where you're never gonna find a balanced tree that looks like this. Where on the left side here, we have a height of 0, but on this right side, we have a height of 3, let's say. So this is too much of a difference. But let's not get too much into that. But anyways, the benefit of a binary tree is quick traversal through a set of data, pretty much.
So I know we haven't learned about Big O yet, but what would be the Big O of this?
This would be log n. So log n is going to be pretty much like the height of the tree, if I'm not mistaken. So we have n is the nodes, so we have 1, 2, 3, 4, 5, 6. So let's say there's another node here, just so. Actually, there can't be. So this is 12, this is 11. So this is a relatively balanced tree. So at most, you will only have to go down 4 levels. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, I'll get back to that on the Big O day, but pretty much this is going to be log n, which is way smaller than n. Way smaller than n squared. If you have to loop through a list twice, it's going to be n squared. But yeah, did that answer your question?
Yes, thank you.
Awesome. And yeah, we'll definitely go into that later on. Okay, so this is trees. There's a lot of different implementations. There's also resources that I will show in a bit. But I wanted to mention one last data structure, which is called a graph. So a graph is kind of similar to a tree, but you have nodes that connect. They can connect to each other. They can have, like, they would start at somewhere and then they would have an end or something like that. It depends on, yeah, there's a lot of different graphs. I just wanted to mention that they exist. Graphs are usually used for, what is it called? Like if you're trying to find the distance between one place and another, like the shortest distance, there is an algorithm that uses graphs where, let's say this is place 1, this is place 2, place 3, and the time it takes to get from place 1 to place 2 is 2 minutes, and the time it takes to get from place 1 to place 3 is 4 minutes, but then this is 2. So if you went 1, 2, 3, it's going to be the same distance as 1 to 3. And there's a bunch of algorithms that allow you to find the quickest distance, like Dijkstra, Dijkstra's algorithm. Oh, yeah, you guys know what I'm typing or what I'm algorithm. Yeah, if you're into algorithms, look it up. It's pretty cool. But yeah, this was just kind of like an honorable mention. Graphs are used in quite a few spaces. Okay, let's stop this share, and I would like to share this again. So here, yeah, so AVL trees are balanced binary search trees. So like I was saying, so built into the mechanism, you would have to handle rebalancing it when you add a node. So if I'm doing just a binary search tree, let's say I'm inserting 10. So that's my root node. I want to insert 5. It's going to the left. I want to insert 3 now. Go left. If I'm inserting 4, where would this go?
On the right.
Where?
On the right of.
On the right of 5. So let's check it out. It actually went to the right of 3. Because 4 is greater than 3, but less than 5. So if I do 6, it will go up here. 7. So yeah, you get the idea. So this one I can add like this. If I want to find 7, this is the path that it traverses. However, if we have the AVL tree, we're inserting 10, then we insert 3, then we insert 6. So you see how it wanted to balance it, because on the right side of that, we weren't going to have any nodes, but on the left side, we already had 2. So it was becoming unbalanced. So the criteria to balance it is how many levels do you have from this node? So if I added 2, which would go to the left of here, this is still not unbalanced because this one has 2 levels here, this one has 1 level, and so the difference between them is just 1. If I added a third one here, where it goes, if I added number 1, actually, let me show you. If I add 4, you won't have to rebalance the tree because here it's still at the 2nd level. But if I added 1, it's going to add a new level, and it will have to readjust. It's pretty cool. I like these visualization tools. Okay, that is pretty much our lecture for today. There's also something worth mentioning. B trees are different than binary trees. So do not get them confused. So B trees, you can add like a degree of how many max nodes. So a binary tree, you only have 2 child nodes. Here you can add multiple. Yes. Who's asking questions? Let's see. Michael?
I had my hand up. If was this, and this is kind of a tangent, but more out of curiosity, was this something that is covered in previous cohorts, or is this a new addition? Because everyone has said in their feedback that data structures is kind of a weak point of some boot camps, but I'm pretty happy that we're covering them now. So I was just curious if you guys just thought to include it now, or
no, this was included. This has been taught every time.
Okay, cool. Well, I'm glad it's still being taught then.
I'm not sure to what extent, but I think we're gonna be teaching pretty much what was taught last time with a few tweaks.
Yeah, totally. Yeah, exactly. This is what we did last time. Just to add to that, yeah, we would love to dive really deep into this stuff. You're totally right that it's a challenge to do that with boot camps.
100%.
Yeah.
Like we're just scratching the surface. The amount of data
Yeah.
structures that actually are out there are a lot, but these are the basic ones that you will probably encounter while interviewing,
Yeah,
even more than actual practice, but
yeah,
you might come across them in practice too.
yeah. And the truth is, like, this is, I would say, like, data structures and then probably testing are the two things that we heard from Romeo's students. They really felt like they wanted to like dig into more once class had ended to prepare for technical interviews.
Mhm.
And I will say that's because like we cover it, but like we don't return to it continuously throughout the course the way that we do with some of the other things.
Yeah.
Because we're focused a lot on like the building skills to build stuff, which are also critical.
Exactly.
So yeah.
Yeah, we won't be spending too much time on the implementations of these.
Yeah.
Just because it's a lot. This is usually an entire semester's course, where you learn how to implement all these different data structures.
Yeah.
But we want to give you guys the tools of at least understanding what these structures do, how they can be used, and then you can. There's so much documentation out there, which kind of is a good segue to this. So, if you want to learn more about graphs, this Geeks for Geeks, Geeks for Geeks is pretty good. They have a good explanation of things, and they have usually pictures and more in-depth topics based on the bigger topic. So if you're interested in any of the data structures here, so there's like arrays, linked lists, and it shows you how pretty much it's implemented, and more stuff on here. I will give you guys this link. Okay, so another resource that we found was this article. Thank you, Adam, for finding it. Data structures and algorithms, kind of as used in certain tech companies. So you can kind of see what different structures are being used for at the moment. So this is an interesting read. It's in the curriculum at the bottom. Okay, last thing I want to mention. So our assignments for today, we have bank accounts, which is object-oriented design, working with classes and stuff, but this is not our main one for today. In the order, we can go data structures first and then the second one. So this is going to be implementing these data structures that we just talked about. So there's some stretch goals with trees, like building trees and hash tables. And there's documentation, and you guys ask us questions.
Oh,